experimental design. So we'll talk about 2 raised to k minus p, fractional factorial design. So you have k factors, but you don't want to do 2 raised to k experiments. You can do 2 raised to k minus p. So as usual, we'll talk about what are these designs, how do you calculate, what is the problem, that is called confounding. So that's a new term you will learn today. And then algebra of confounding and other designs, and what is the design resolution. There are lots of new terms. You have a question? Okay.
So all of those designs also are just for categorical.
Yes, so the next one, actually that is coming up. The thing is, yeah, okay. So the special case of experimental design when it is continuous, you can make that categorical, right? Or you can just use the regression, which is infinite range. And so we started with regression, which is most people already understand, and now we are going to categorical because, so suppose you go from here to there, you could go continuously, or you could go just 3 steps.
Isn't the experimental design supposed to help us determine how many experiments and what?
Yeah. Okay, so the thing is, hold on. How many experiments is not an absolute question and absolute answer. That is basically, it helps you decide. So basically what is going to happen, suppose you have a continuous range. You could do infinite experiment. And if the mathematics tells the infinite experiment, you won't do it anyway. So the idea is, you decide that I'm going to do 10. So that would be a 10 categorical range. Or you could do 3, like we said, right? And from 3, you could go down to 2, or you could do 2 and then go down to 3 and 4 and 5 and 6 and 10, either direction. But mathematics will not tell you exactly how many you want to do. It is the money and the time. And then for that money and time, mathematics will tell you how much you lost. I mean, this is what we are going to talk about. If you do fractional factorial, then you're going to lose something. So mathematics can tell you all that, but you have to make the trade-off.
So basically, you just decide on if you will be straight values, so this is not a level 2,
Yeah.
lower than 5.
Maybe. The thing is, this is where the system thing comes up. If you know that this is unimodal, then the lowest highest will do. If you know it is like this, you need to do either these 2 or you need to do 3. Right? So system knowledge always takes precedence over mathematics. I'm just keep telling you throughout this course. And that's the differentiator for this whole book and this course, is that most books are written by mathematicians. And they don't really emphasize the real world things. And I was actually in some sense a real world person who had done 7 years of real industry research, not research actually, I was doing real hands-on performance analysis for a company. And so then I realized that there is a disconnect. All right, so let's see. So when you do 2 raised to k minus t, when you have a large number of factors, k is large. And so that will mean that you will do large number of experiments if you do full factorial. And so you decide to do fractional factorial. Now, it allows you to analyze k factors with only 2 raised to k minus t experiments. Now, there we go. Alright? So, for example, if you do 2 raised to k minus 1 design, you can do only half as many experiments, 2 raised to k minus 2, only 1/4, and so on. So here is a 2 raised to 7 minus 4 design. So how many factors are there? 7. And how many experiments they are doing? 8. So they are going to analyze 7 factors with 8 experiments. So these are the factors A, B, C, D, E, F, G. Now these are the 8 experiments, 1, 2, 3, 4, 5 to 8. And these are the values they are going to use. All right? 7 factors with 8 experiments. And you notice that we have -1 + 1, -1 + 1, and so on and so forth. And this is a very good design because this has many properties that we want to look for in a design. So let's see what those properties are.
How big is it?
Yeah, how? Coming up. So, first of all, why did we do full factorial design and why did we put -1 + 1? Because there were several properties. First property was each column was adding to 0 before in full factorial design. And the columns were all orthogonal. When you multiply 2 columns, they will become add up to 0 too. Alright? And the sum of these square of the column y equal to 2 raised to k. So everything was 1 and added up 2 raised to k. The same thing applies to this design. Although you don't know how I wrote it, but you can see every column adds to 0. Every column is orthogonal to the other column. You multiply these two and add up, they will add up to 0. And obviously you square and add, they will add up to 8. So this actually satisfies all the properties that we had before, right? So what's the magic about? The magic is this is actually a 2 raised to 3 design. If I were to ask you to write a 2 raised to 3 design, you will start with 0, 0, 0, 0, 0, 0, 1, 0, whatever, right? Write the 8 rows. Then you will write BC, AB, CD, BCD, whatever, 8 columns. So I've done exactly the same thing. But instead of writing here AB or whatever that is, I wrote B. So I just changed the column heading. That's the only thing I did. It's the same 2 raised to 3 design. Yeah. Yeah. AD, BC, ABC, ABC, something like that. AD, AC, BC, ABC. So the same old 8 columns we use, so all these properties remain. Right? And now the advantage is, so we can use the previous formulas, we will get exactly the same thing. Each effect is equal to the product of Y column and the column, that vector there, multiply, divide by 8. Multiply, divide by 8. You can get QA, QB, QC, QD, everything. So we do that. So here is an example. This is the Y value. These are the 8 columns, and we added an I column as usual. And then we multiplied and added up, divided by 8. So now you can say that the A effect explains 37%, B explains 4%, and so on and so forth. Yeah.
So you're actually ignoring 4 factors? Or are they?
We are ignoring some interactions.
But aren't you ignoring factors?
No, we are ignoring ABCD, all 8 factors are here. But what is not here is AB, AC, BC, and ABC. And going on, AD, AE, whatever interactions. So there are no interactions in this design right now.
So you are ignoring all of the interactions.
All the interactions being ignored. At least in this example. We will show you how to add more interactions in here. But the idea is that if you could ignore the interaction, then instead of doing 1 factor at a time design, remember 1 factor at a time design, then you just keep a central thing and then you just change 1 factor. When you come back, change another factor. For 7 factors, this will require the same number of experiments. That 1 factor at a time design will require maybe 7 or 8, right? And this is the same thing, but this is much more statistically powerful. That we'll see in a minute. Where is 37%? So how do you get the percentage? Anybody remember how do you get percentages from here? Yeah, you have to square this and divide by, yeah. So SST will be sum of these squares. And I mean, you can look at that. Basically, the factor that has the highest impact is C and A. Everything else, E is negligible almost, and these other things are negligible. So now, from this 8 experiments, you can conclude that if you really had more time, what will you spend on? What factors? C and A, right? And if you needed to do 3 levels, you know, those are the factors that you will do 3 levels on, rather than spending your time on E. You see what I mean? So this is what the advantage of this fractional factorial design is, that you can put hundreds of factors there and then figure out which are more important, and then just do a bigger design with those factors. Now interactions are coming up. Yeah, no, that's the low goal. Is that whenever you do something less, you give up something. I mean, there's always a trade-off. So here we are giving up something. So let me go to the interactions in a minute, but before I do that, let's do the sign table. How do you make these tables? So I just showed you one example, but that is not the end of the world. Basically, there are lots of other ways to do this thing, right? So prepare a sign table for k minus p factors. So you could do, for example, 2 raised to 7 minus 1, not minus 4. You could do 7 raised to minus 1. How many rows will it have? 2 raised to 7 minus 1 is 2 raised to 6. That is 64 rows. Right? For that, what will you do? You will make a table for 6 factors. Right? So make a sign table for k minus p factors. And obviously, sign table, the first column would be I, as before. And mark the next k minus p columns with k minus p factors. And of the remaining on the right, choose p columns. Now you will have lots of columns. In that 2 raised to 6, 7 minus 1 design, you will have 64 columns plus 1. Right? Out of those 64, you can select as many as you want. Okay? And so you choose p factors, and that's it. So you have lots of possibilities. All right? So let's take this example. First, before we go to the new example, this one actually was done as before, is that we wrote a 2 raised to 7 minus 4, 2 raised to 3 design, and AB, AC, BC, AC, and then we just replace them with the remaining 4 factors, D, E, F, G. But in a bigger design, you will have more, even more. So here is a 2 raised to 4 minus 1 design. So there are 2 raised to 4 minus 1 design has 8 columns. Now you have to put D somewhere. First 3 are fixed, A, B, C, because you are doing 2 raised to 3 design. Question is where to put D. D could be put here, 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 here. Okay. If you don't have any further information, then the best place to put it is at the highest interaction. So what we are assuming here is that the ABC is negligible, while AB, AC, and BC we will find out. We will find out D too. But ABC is negligible, so therefore that column will be used for D.
So why is it important to choose D if it's
Yeah, so that is coming up too. Is that what if we put D here, or here, or here, or here? I'm just saying, before we get there, a normal guideline would be that you take the interaction that you think is negligible, which is generally the highest order interaction, and put the factor there.
So I'm trying to understand why the location is significant here. Why is it,
Why is what?
Why the location of D?
Yeah, okay. Please hold on to that question. Any other question? Okay, so basically, right now I'm just saying that do it, and this is it. And the question is why? I haven't told you. So you take the highest interaction and put the factor there. If you add one more factor, you will put the factor here, and so on and so forth. I mean, it doesn't really matter which second order interaction you put it, but whichever you think is small, put it there. So what is happening is confounding. Confounding means if you were to calculate QA in that design, the QA would be this column value. If you were to calculate QD, it would be this value. You can just look at the sign, and then I just wrote the signs there, right? Now, if you were to confound QABC, it will be exactly the same value because ABC has the same signs as D. Right? So what you have done is you have gotten QD and QABC all mixed up. And that is called confounding. So when you get that effect, you don't know whether it is QD or whether it is QABC, or how much of this is QA, you don't know that. But if you assume that the QABC, so basically what you are getting is the sum of those two, and if you assume that this is negligible, then you can assume that this whole thing is QD. So if you know QABC is negligible, then this is a good design. If you know QABC is non-negligible, then this is not a good design. Yeah, that is the system. The thing is, what is going to happen is, some of these things you can, if you know from the system that these two things don't interact, for example, my height may not affect what response time I get, so I may not worry about the interaction, right? Something like that. So if you know something about the factors that these two things will certainly affect each other, but this will not, so then the factors that don't interact, those are the columns that you want to use for new factors. Alright? And if you're not sure, then just increase the design. I mean, you can just put 2 raised to 4 design rather than 2 raised to 4 minus 1 design, and then you will get all the interactions. Which is also you can do basically if the number of factors is small. And this is, by the way, only first phase design. They always do 2-phase design. First phase is you keep the number of factors large, but you are ignoring a lot of stuff in terms of interaction. In the second phase, now here's the thing though. I mean, so what we are assuming is that the factors that have a large impact, like C in the previous case, probably its interactions are also could be large. But the factors that have small value, like 0.5% for E, probably its interactions are also small. I mean, just when the factor, right? So these are some of the assumptions which may not apply to your particular system. So that is where you have to apply your system knowledge to say that, yeah, but normally speaking, the interactions are generally smaller than the factors. Yeah. Yeah.
It shows to keep all the main factors. Is that not always the case?
No. No, I'm sorry. You will keep all your factors, but we did not keep any interaction. So that is not always the case. Sometimes we keep the interactions. Like in this design, we keep some interactions.
So the main factors are always the same.
Of course, if it is a factor, then we have to analyze that. You have to analyze that. All right. Now, this is not the only thing which is confounded. D and ABC is confounded, but there is more. You write down this thing, D equal to ABC. That you already figured out, right? When you wrote the column, D equal to ABC. Now you will find out that A actually is confounded with BCD, because if you were to calculate BCD from that table, you find that that has exactly the same signs as A, and therefore A is confounded with BCD, and B is confounded with ACD, C is confounded with ABD, AB is confounded with CD, and so on and so forth. There are a total of 8 confoundings. Okay? And I is confounded with ABCD. Your mean has the 4th order interaction. Alright? So this is the whole set, and it turns out that you can get the whole set from here. How? Well, before I get there, let's just see, just to verify that you can verify that I is equal to ABD. Take A, B, and D. Multiply those, you will get I in column 1. It's not shown here. A equal to BD, you take D, which is minus 1, and D is plus 1. Multiply those, you get A. A equal to BD, and so on and so forth. This is actually another design, not the previous design. This is another design. Its confounding are written here. And this is not as good as the previous design. The previous design was this one. And this is another 2 raised to 4 minus 1 design. Here what we did was we put D equal to AB. Right? Since we put D equal to AB, this resulted in these confoundings. Now the problem with this design is that most factors are confounded with the second order interaction. Two-factor interactions. Alright? In the previous design, most factors are confounded with the third order interaction. Which do you think is smaller, third order or second order? Generally, third order is smaller than the second order. Second order is smaller than the first, factor itself. And therefore, this design is better because you can quickly, we can easily assume that ACD is smaller than B, so most of this is B. But here, we are assuming that BD is smaller than A, and so we are, A we are going to get. But the thing is, it's better to assume that BCD is smaller than BD is smaller. And therefore, this design is not as good. Same number of experiments, same number of factors, but the designs are different because the confoundings are different. Now, yeah. AD equal to CD right here, yeah.
On the previous slide, correct?
On the previous slide, yeah.
So what would you do?
Yeah, in that case, basically, you don't know the difference between those two factors. There is no way, that design will not tell you. And if that turns out to be large, if it is small, you forget it. You don't want to divide it into two small ones. Suppose it is 90%, then you really need to work out more work to figure out so that AB and CD are not confounded. Right? Yeah. Multiply which columns? Okay, so the thing is, if you want to find out the factor B, what columns do you multiply? B with Y and add it, right? That's what I said, multiply. This is QB. Right? And when you want to do ABC, you will do the same column and multiply by Y, get the same answer.
Will it be the same Y?
Yeah, it will be the same Y. The thing is, because ABC is equal to D. In this design, D equal to ABC. So if you were to write a column for ABC, it will have the same values, and will have, when you multiply with Y, you will get the same values for ABC. So really what you're getting is something which confounds B and ABC, which is combines those two.
I don't understand, because I thought when you're adding D, when you're replacing ABC with D, it means that you're actually adding D to your experiment, and then your Y will be different because you're taking under consideration the new possible.
Okay. If you were doing a three-factor design, then yes, your Y would be different. Because you will put these three, this is the column that will decide the values of the factors, not these columns. The first three columns will decide the values of the factors and then the corresponding Y's. This is a four-factor design. So these three columns plus this column decide what are the values of the factors. So the Y values would be different. In a four-factor design, the Y values will be different than the three-factor design. Yeah. And 14. Okay, I'm going to tell you how in a minute.
Oh, okay.
Right. Everything first, I want to give you an example, give you how to do it, and then tell you why and everything else. If by the end of this chapter you're not done, this is actually one of the most interesting chapters, by the way. And I wanted to do this before you started on the project because many people use this thing, experimental, and most of the people who do real measurement projects, or have done in the past, they have used these chapters because to their advantage. And so algebra of confounding, how do you find out that whole set? Well, it is very simple. You can write down any confounding that you know about and then multiply by one factor at a time, and then or two factors or whatever you want to multiply by, the only rule is that the square equal to 1. So if you write down I is equal to ABCD, multiply both sides by A, you get A is equal to A square BCD. Right? A square is 1, so you get BCD. Multiply by B, what do you get? B equal to what? ACD. And multiply by AB. AB equal to what? CD. Good. You got it. So this is the algebra, and this is how you can figure out all of the confoundings. And this is called generator polynomial. The I equal to whatever it is called the generator polynomial. For the first design, I was equal to ABCD. In the second design, I was equal to ABC. Alright, both of them have the same level number of confoundings because you can keep multiplying by all the products. But this one actually has a lower resolution because the third order interaction is getting confounded with the mean. Here the fourth order interaction is getting confounded with the mean. So this is not as good a design. Now, normally, if you knew that ABCD is very, very big, then obviously you don't want to confound that with anything, and so that is the case. But generally, ABCD would be the smallest of all the things that we know about. Highest order interaction. In the 2 raised to 7 minus 4 design that we had done, the interactions are even bigger. So in that case, what we have done was we have written B equal to AB, E equal to AC, F is equal to BC, and G equal to ABC. We have replaced these columns like this. Now you can keep multiplying each of these 4, and you get 4 new confounding. For example, if I multiply by D, what do I get? D square is equal to ABD, which means I equal to ABD. D square is 1. So we get I equal to ABD, I equal to ACE, I equal to BCF, I equal to ABG. That means all of these things are confounded together. I includes not only itself but ABD, ACE, BCF, ABCG. So the third order and the fourth order interactions are confounded with the mean. And in fact, you just keep doing this. This is not the end. Basically, you will get this whole thing. I is confounded with these 16, total 16 effects, because what you did was you had 2 raised to 7 minus 4. You saved your work by a factor of 16. Because you saved your work by a factor of 16, you have 16 times more confusion. Okay? However, that confusion is okay because your time is money, right? So you are saving money, and if these things are all small, why waste time on those? Alright? So when you do 2 raised to k minus p design, you are saving your work by a factor of 2 raised to p. And you will have how many terms like this? 2 raised to p. With every effect that you estimate, there will be 2 raised to p minus 1, I think, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, yeah. 15 other effects that will be right there. And on those 16, you can say the same thing because A is confounded with 16 other things. Okay, 16 total things are confounded together. Alright, so this is why now we have the term called design resolution. Design resolution is the order of the effect is the number of the terms. So for example, order of ABCD is 4, order of I is 0. Right, order of ABC is 3, order of AB is 2. So when you have this AB is equal to CDE, the order is 5 because you are confounding 2 and 3, 5. So the minimum of these confoundings is the resolution of the design. So for example, this design, if you were to see, this is order 4, everything is 4. The minimum is 4. And therefore, this is a resolution 4 design. ABC equal to? Yeah, that is 4. 3 plus 1. Okay. Now, in this case, all of them are 4, right? But that is not always the case. So let's see another example. This one, I equal to ABD. Now, you say I equal to ABCD has a factor 4, right? 4, but I equal to ABD has 3. So this is a resolution 3 design. You look at the minimum. What you're saying is that third order interaction is getting confounded with the mean. Whereas in previous, only 4 order interactions were confounding with the mean. Right? So this one is, sorry, where am I? Yeah, this is the resolution 3 design. And so this is not as good as the previous one, which is resolution 4 design. Resolution 4 design is better because you are taking bigger interactions and causing the confusion. The design of high resolution is considered a better design. Now, every time I want to emphasize, and you will hear 15 times a day, is that this is what mathematically is true. But in your system, there might be some special cases where the interaction, when the 4 factors meet together, there is certainly an outlier shows up. So that is where just don't go blindly behind the math. Okay, so now we show you case studies, and there are plenty of case studies I can show you. You can read them on my website, but this is one of the earliest one. Latex versus troff. Now, most of you have heard latex probably, but not heard of troff. Troff, I think, is what I wrote my thesis in 30 years ago. That is the text setting system. That was the only text setting system where if you wanted to write A sub B, there used to be a way to do that with troff, and that was the smartest thing you could do. And the only printer we had was typewriter. So it will type A, go down a little bit, type B, come back up. There was no font sizes. One size, all fonts. It was a typewriter. Right? troff was that editor. And so somebody wanted to compare latex with troff. And so there are 2 factors. There are actually A, B, C, D, 6 factors they wanted to compare. 6 factors. The factors are the program itself, how many bytes is the text or the document, how many equations are there, 0 or 10, how many floats. Everybody knows what is a float. Float is a figure. 0 to 10, 0 and 10. Tables, how many tables are there, how many footnotes are there. Okay, 6 factors, each at 2 levels, and therefore we need some help out of 64 experiments. So they decided to do 2 raised to 6 minus 1, not much help, but that is what they decided. 2 raised to 30, there are 32 experiments. And obviously they selected the design which was A is equal to B, C, D, E, F. Actually, they could have done a better design. But anyway, this is A equal to B, C, D, E, F. And you can make the table now, right? Everybody can make the table. How will you make a table for 2 raised to 6 minus 1 design? For 5 factors, you make a table, there will be 32 rows. Then the only thing you will change is You have, so let's say those 5 columns you labeled A, B, C, D, E. Now F is not labeled. For this design, F will be equal to how much? Can you say F equal to what? Right? Multiply both sides by F. What do you get? B, C, D, E. So take the B, C, D, E column and put F there. That's your design. Right? And each factor will be confounded with some other factor, with some other interaction or whatever. So you can write those things as well. So here's the summary. For the 5 factors, these are the effects and this is the interaction which was significant. You see, 39% highest, 24%, 15%, 14%, and F. Right? A, B, C. D is not even in the table. D is probably here. I'm coming to you. So one thing you notice is that D you can forget. It is negligible. F is sort of negligible. E is small, but AC is big. Right? Now AC is confounded with something which we can figure out. AC is confounded with what? AC is confounded with, multiply both sides by AC, what do you get? A, B, D, E, F. Now we can assume that is very small, that A, B, D, D, whatever, big number. So most of it is AC. It is 14%. Okay, multiply both sides by AC. What do you get? A, B, D, E, F. Right? Now A, B, D, E, F. 5-factor interaction. A, B, D, E, F. Right? And maybe the reason these students, by the way, this is from MIT, these students selected this design is because they knew that this interaction is large, or some experiment showed them, so they just didn't want to have this interaction confounded with some 2 or 3 order interaction. Now this one confines AC with 5th order interaction. And so now they know this is more important than D. Actually, I don't know really how they came to this design. Just like you will do your experiments and you will come up with some solution. These guys did their project and came up with this thing. So with this design, it is really interesting to find out that there are some factors that you can forget for the next phase, and there are some interactions that you cannot forget for the next phase. So over 90% of the variation is due to bytes, programs, and equations, and the second-order interaction. Those are the 3 things, and the second-order interaction. Text file sizes were significantly different, making its effects more than that of the programs. And so that is another thing is that to go back, bytes. You really don't want to. This is workload, and most of these are workloads. They really were interested in the program, not in workload, but it clearly says that the workloads do affect, and this particular workload factor had significant difference, 2,000 to 25,000, and therefore the difference is so big. Higher percentage of variation explained by the program times equation interaction, of course that AC, and the choice of the text formatting program depends upon the number of equations. So here's the thing, basically if you have lots of subscripts, these things on equations, then you will use, I think Latex probably. I'm not sure right now. I'll have to see the signs. Here it is actually. TRAF is not good for equations. Okay? So anyway, this is very powerful, the fractional factorial design. And particularly if you have a large number of factors, you can sort out with a small number of experiments, which is what is most important, and then concentrate on those. All right, I think we're done with the case study, so we finish the summary. Summary is fractional factorial design allows a large number of variables to be analyzed with a small number of experiments. First result. Second is many effects and interactions are confounded. The only thing is you lose is because you can't get every interaction. You lose some of the interactions. But if you lose higher order interactions, that might be okay. The resolution of a design, now you know. Now you know which design is better and why it is better. And now you know how to write a design too. Right? Everybody feels comfortable with writing design? If you do, then obviously I'm going to ask you to do that. And actually I'm not asking you to write the design. Design is already written here. You have to analyze it. You have to analyze it, write down the columns, write down the values, find out all the main effects, percentages, confoundings, better design, and what is the resolution of this design.